Principal engineer for 20 years at Endicott Interconnect Technologies with a focus on microelectronics packaging development for high-performance computing, medical, and quantum electronics. He's now a member of the technical staff in the Quantum Information and Integrated Nanosystems group at MIT Lincoln Laboratory. Robbie?
Thanks, Paul. Thanks for a nice introduction. My name is Rubindra Das. I'm from MIT Lincoln Lab. And today I'm going to talk about wafer-scale superconducting MCM. So superconducting multi-chip module is a platform for chip-to-chip communication. It can be used for superconducting qubit, for SFQ chips, for CMOS chips, for photonic chips, or you can combine them together in a single platform. Particularly, we are interested for superconducting MCM is important for heterogeneous integration. Here I'm showing you few references related to our SMCM work. For example, this paper was talking about how MCM is used for cryogenic computing applications. This one is talking about ELAC, which is a new way of chiplet integrations. Then we have Elastic, which is a very large active MCM. Then we have a wafer scale platform. We do die-to-wafer integration and many more. But today, I will talk about SMCM and how can we fabricate larger MCM beyond radical size and eventually full wafer MCM. So here's outline of my talk. My talk will answer three important questions. Question one, what would be the largest MCM we can build using single mask exposure, which can repeatedly maintain impedance control line? Question two will be, how can we combine multiple MCMs together? And question three, what would be the best possible way to fabricate wafer scale MCM? But before answering to these questions, we would like to know about superconducting electronics and why do we need superconducting MCM for high performance computing. Superconducting electronics useful for developing next generation low power computing technology because of their ultra low switching energy and fast switching, something like this. Currently, we cannot scale individual superconducting chips, so we need to develop wafer scale MCM to provide useful capability. Now, superconducting MCM provides high bandwidth, speed of light, nearly lossless chip-to-chip communication. It can be aluminum-based or niobium-based superconducting MCM. In our traditional superconducting MCM, we use 4 niobium metal layers and 1 embedded resistor layer. So the process flow for fabricating MCM is basically you start with a full wafer MCM with underbump metal, then deposit indium bump onto a MCM wafer on top of UBM, and then dice individual MCMs from the wafer and bump bond with known good die. Our process uses micro bump only on the MCM side, which allow us to select known good die from any suppliers as long as their die has pad metal compatible for soldering. As I have mentioned that we are depositing indium only on the MCM side. So start with MCM with micro bump and then bump bond with a test chip. So here is indium bump on a superconducting MCM. Then we are bump bonding with test chip. Test chip could be qubit chip, could be CMOS, could be SFQ, could be photonic chip. Then you can do cross section. And here you can see indium bump electrically connect MCM to the test chip. Our MCM packaging is like a turnkey solution. You submit your design, we will deliver you the final product. Once you submit your design, we will do wafer layout, mask ordering, MCM fabrication, and most of the cases, we also fabricate superconducting chips. Sometimes we get known good die from outside. So once we have MCM and known good chips together, we will do in-house assembly and characterization before sending it out to the collaborator for module level testing. Now, over the years, last probably 5-6 years, we have already fabricated more than 300 MCM wafers, delivered over 500 devices. Today, many industries and universities are using our devices for either qubit or SFQ or CMOS or photonic integrations. Overall, we can say our superconducting MCM technology is very robust for cryogenic applications. Currently, MCM technology demonstrated 16-chip MCM, but this is not enough for superconducting electronics. We need large number of superconducting chips for system demonstration. And for that, larger MCM will be better. So our objective is to develop large MCM beyond current size by using single mask exposure, by stitching multiple masks, and by combining multiple lithography. So this slide shows MCM process flow, starting from microbumping to flip chip bonding to packaging to electrical characterization. But one very, very important thing when you do a wafer scale platform, you need to make sure that you're designing correct bump configurations. So the bump design micro bump design is going to be very, very critical. So here we have designed and fabricated a bump stack up with the 1 micron like niobium. So a little bit niobium pillar, UBM, and then niobium, UBM, and then indium on top of that. So this kind of micro bump configuration will be very, very critical for bump bonding a very large chip, like over here, 20 millimeter by 20 millimeter chip. And also the bump bonding yield is going to be very high. So here we have yielded up to 100K bumps. So this approach produces high bump bond yield as well as low interconnect resistance. We're getting interconnect resistance at 4K for this kind of structure is about 50 to 100 micron, which is around 2.5 to 5x smaller than traditional indium bump interconnect resistance at 4K. So this slide will answer our first question. The first question was, what would be the largest MCM we can build using single I-line mask exposure? For I-line mask, the largest print will be around 52 by 52 millimeter. To avoid any lens edge degradation, we select 48 millimeter by 48 millimeter field size as our largest MCM, which can print 0.8 micron wide 50 ohms line across the MCM for chip-to-chip communication. There are multiple CD cells you can see over here. And this CD cells is basically confirming that we can print 0.8 micron line. Here image shows 48 millimeter by 48 millimeter MCM diced out from 200 millimeter wafer and bonded with 20 millimeter by 20 millimeter chip. So why are we choosing large superconducting chip? As you know, that one 20 millimeter by 20 millimeter chip and 16 5mm by 5mm chip will have same chip area, but 20mm chip will have a larger active circuit area than 16 individual 5mm chip because it doesn't have edge keep out area for dicing as well as inline metrology for individual small chips. In general, one 20mm chip can have larger active circuit area than 16 individual 5mm chip for a given lithography. Now, time to answer question number 2. How can we combine multiple MCMs together? We have developed an optimized mask stitching process to combine multiple MCM together. So here you can see there are 2 stitched MCM demonstrated. One used 35mm by 35mm field size to create 70mm by 70mm stitched MCM, and other use 48mm by 48mm field size to create 96mm by 96mm stitched MCM. We have also used SEM micrographs to show 0.8 micron 50 ohms niobium line at the stitch boundary. And we measured room temperature line resistance to understand stitching impact. And what we found, room temperature 0.8 micron snake and comb lines, resistant with or without stitching, is showing similar type of resistance for many, many wafers. All these data indicate that we can control impedance line width at the stitch boundary. But stitching will reduce MCM count per wafer. For example, 200mm wafer can produce 16 35mm by 35mm MCMs. But it will only make 2 to 3 stitched MCM within a wafer. Similarly, for 48mm by 48mm MCM, one wafer can have maximum 6 to 7 MCMs per wafer. And it's going to be only one stitched MCM for 96 by 96 field size. So we did see wafer real estate usage issue as you go from traditional MCM to a stitched MCM. And wafer scale MCM might be the approach to utilize entire wafer real estate. Next slide will answer our third question. So what would be the best possible way to fabricate wafer scale MCM? Based on our experiments, we can say combination of I-line stitching and direct write lithography can produce high yield, low cost wafer scale MCM. Here you can see process flow from single MCM to wafer scale MCM. So what will happen when signal goes from single MCM to stitched MCM to wafer scale MCM? For single MCM, impedance control lines are within MCM for chip-to-chip communication. For stitched MCM, impedance control signal lines has to travel from one MCM to the other through the stitch boundary. And then direct write wafer scale routing takes the signal from the stitch boundary to all the way to the edge of the wafer. So it is important when signal goes from one end to the other end of the wafer, through many stitch boundary, there should not have any impedance discontinuity at the stitch boundary. So this is about wafer scale MCM. The next step is once you have a wafer scale MCM, once you have a flip chip integrated wafer scale MCM, how you're going to create a wafer scale system, or how you're going to do a larger system demonstrations. What are the possible way you can do that? And one possible combination will be that start with your wafer scale MCM, do flip chipping. So this is an example of wafer scale MCM assembly approach. Here, flip chip bonded wafer scale MCM can produce system on a wafer, and assembly of wafer scale MCM with wafer interposer wafer combination can be used for bigger system demonstration. So with this, I would like to summarize my talk. So this talk answered three important questions. Question one, what would be the largest MCM we can build using single mask exposure for 50 ohms line? And the answer is 48 millimeter by 48 millimeter. Question two was, how can we combine multiple MCMs together? We developed an optimized stitching process to combine multiple MCMs together. And the third question is, what would be the best possible way to fabricate wafer scale MCM by combining I-line stitching and direct write wafer routing process? And finally, I would like to acknowledge our group and sponsors. Thank you for your attention.
Okay, so the question was, what's the diameter of the indium bump?
We are making 5 to 15 micron.
And what's the bump pitch?
10 to 35.
So this 48 mm by 48 mm, is that the single eye mask exposure limit?
Yes,
is that
yes,
the instrument that you use, or it is across the across all the? This
is for 365 nanometer litho. Yeah, this is a standard everybody is using for a single mask process. You can go like 52. I told you 52 is the print size, but if you want to avoid, you might go up to 50 max, but 48 is more like a comfort zone.
I see. And do you know if the litho machines have a roadmap of going finer, like getting to a bigger exposure, like getting into bigger, more than 50 mm by 50 mm in a single exposure?
Yeah, that 1X can do it, but again, the controlling line width is one of the big factor. That when you have a 50 ohms line, you need to make sure that across the MCM, the line width variation is very, very critical. As long as you can maintain a very tight control, line width should be fine. Based on our equipment, we did see that the line width variation, because you can do even 1X mask, or you can use nowadays Heidelberg, which can print even a smaller features and can print like a maskless approach. So you have to take into account many things, how much time it will take to print a very high density circuits on a wafer layer, and then also how the line width variation as you go from one edge to the other edge. So all these things will you need to take care of that. And eventually when you do manufacturing, maybe you can come up with some better options.
Yeah, sounds good. The other issue is like when you stitch the MCMs together, are you limited by the is warpage a concern, right? Like how many MCMs can you really stitch together?
It's not the warpage, because it's a stitch boundary is a concern. So when you do we're doing 4 masks per layer. So 4 masks per layer will have a 4 stitch boundary. So as you increase more and more increasing number of stitching process, because we tried that with actually EX4 radical with 22 millimeter by 22 millimeter. More stitching means your yield issue is going to be more and more. You can create more defects. So you can go beyond 4 masks per layer process, but that will be more challenging for reducing yield. Also, we would like to reduce the stitch boundary also, because that's where you will see most of the variation in line width, and also the yield challenges are going to be there at the stitch boundary.
Yeah, one quick thing. So currently your MCM, how many layers is it supporting? You said it's 4 routing layers, or?
So four routing layer and 1 resistor layer. Now we're going to 6 routing layer, 1 resistor layer, and then the next mask is coming up with 9 routing layer.
Thank you very much, Dr. Das, for presenting an excellent presentation.